Okay, so good day everyone. So the contents of my lecture for today is about Graham's law of diffusion and diffusion. Second we'll have problem solving for the law of diffusion and effusion. We're also going to derive the equation that relates the rate of diffusion and diffusion to the molecular weights of the gases. Okay. And then we'll have Dalton's law of partial pressure. Okay, so your Graham's law of diffusion. Okay, so diffusion is the mixing of gas molecules by random motion under conditions where molecular collisions occur. So it is from higher concentration to lower concentration. Okay, so for better visualization of what Graham's law of diffusion is, okay, so we have here a GIF. Okay, as you can see, we have two different gases here. Let's say this is gas A and gas B. Okay, so you can see the molecules of gas A moves from the left side to the right side, and the molecules of gas B moves from the right side to the left side. Alright, so this movement occurs until it reaches the state of equilibrium when the concentration of gas A and gas B are equal. Okay, so that is the Graham's law of diffusion. So what is the difference to the effusion? Okay. Your effusion is the escape of gas through a pinhole without molecular collision. So imagine if we had the same container, okay, we had the same container and we had the same gas A and gas B, and we have a barrier between them. Okay, imagine if that barrier is poked in the middle and only a portion of that is the escape points of gas A and gas B. Okay, so that is the difference. Since the diffusion, we allow it completely open. Okay, in here sa effusion, we only have this pinhole. Okay, all right, so that is your effusion. So your Graham's law of empirical relationship, it states that the ratio of the rates of diffusion or effusion of two gases is the square root of the inverse ratio of their molar masses. Okay, so kung paano natin yan isusulat in terms of mathematical equation, so we have the rate of diffusion or effusion of gas A, okay, is equal to the inverse of the square root of the molar mass. Okay, so that is square root of molar mass of gas A. So if we are to relate that to the rate of diffusion or effusion of gas B, it's also the inverse of its molecular mass. Okay, so paano nangyari yun? Okay, so we have the relationship that is based on the postulate that all gases at the same temperature have the same average kinetic energy. So we recall that as a result of the kinetic theory of gases, that the temperature in degree Kelvin is directly proportional to the average kinetic energy of the molecules. Okay, so we can write the expression for the average kinetic energy of two gases with different molar masses. So what is the formula for the average kinetic energy? So we have the kinetic energy for gas A, that is equal to 1/2 mv squared Okay, that is velocity of gas A, mass of gas A, okay, and kinetic energy of gas B, that is also 1/2 square. Okay, so since from the result of kinetic theory of gases, the temperature in Kelvin that is directly proportional to the average kinetic energy, we can equate that the kinetic energy of A is equal to the kinetic energy of B. So we have 1/2 ma dA squared is equal to 1/2 mb vb squared. So this cancelled out. Okay, so relating the um, masses of the two gases, we have ma over mb, that is equal to v squared over v squared. So taking the square root of both sides, we have uh, vb over va is equal to the square root of mass A over mass B. Okay, so it's also the same to the average kinetic energy, or the velocity of the gases A and B is also the same as the formula for the rate of the diffusion or effusion here. So, or formula here. Okay, so under the same conditions of temperature, pressure, and pressure, the rates of diffusion of different gases are inversely proportional to the square roots of their molecular masses. So we already derived this. Okay, so the rate of diffusion of gas 1 over the rate of diffusion of gas 2 is equal to the square roots of the ratio of the molecular weight of gas 2 to the molecular weight of gas 1. So in other words, okay, the lighter the gas molecules, the faster it will diffuse. Okay, from that relationship, we can see that it is inversely proportional. Okay. Also, the solubility coefficients of the gas also plays a role in its diffusion rate. So this is a measure of how easily the gas dissolves in the liquid. Okay. So the more soluble the gas is, the slower it will diffuse. This is because the gas molecules are likely to dissolve in a liquid rather than move through a membrane. Okay, so based from the definition of the Graham's law of effusion, okay, the relationship of the rate to the molecular weights, we can also have different equations for that based on the definition of your density and the rate. Okay, so substituting the rate here, rate 1 is equal to volume 1 over T1, right? So if we are to substitute that, rate 1 is equal to volume 1 over T1, rate 2 is volume 2 over T2. Okay, since we're talking about diffusion here and we assume that there is only one container, the volume is equal, so we can cancel this out, and then we can have T2 over T1, which is equal here, and we know that R1 over R2 is also equal. to this. Same is true to our density. Okay, so density is equal to m over v. Since we have the same volume, it is cancelled out. Okay, so that's fine. Okay, so let's have some example regarding diffusion. So if a gas diffuses at a rate of 1/2 as fast as O2, find the molecular mass of the gas. So you can pause the video if you want to solve this on your own. Okay, and then after that we can solve it together. Okay, so we write the given first. We are given the rate of diffusion 1, which is 1/2. Rate of diffusion 2 is 1, which is of course the reference here. We are only given the rate of diffusion of one gas, but of course we must have a reference for that, for the gas 2, which is 1. Okay, so we are also given the molecular formula for the gas. Then we can now solve for the molecular weight. Okay, so our required is molecular weight of the gas 1. So using the formula, we substitute here, then we can get the value of your molecular weight 1, which is equal to 128 grams per mole. Okay, alright. So let's have another example. So a liter of gas diffuses through a pinhole in 20 minutes. The time necessary for the liter of ethane to diffuse through the same hole at the same temperature is 19.4 minutes. So we are asked to calculate for the molecular weight. So we have a pinhole. So ibig sabihin, this is a problem regarding effusion. Okay. Writing the given, we have T1, 20 minutes, T2, 19.4 minutes, and the molecular weight of 2, 32 grams per mole. Okay. And we have this formula na dinerive natin kanina. Substituting everything, we can calculate for the molecular weight 1, which is equal to 30.1 grams per mole. Okay. Let's have another example. So try to solve this, and then you can check your answer. Okay. So we have a given T1 is equal to 146 seconds, T2 115 seconds, molecular weight for that gas 2 is 44 grams per mole. But that is carbon dioxide, so you already know how to get the molecular weight of that. Okay, and we are asked to calculate for the molecular weight of molecular mass of A. Just substitute everything. So never mind this 50 ml, because you know we are only talking about a single container, so the volume does not change. Okay, so M1 MW1 is equal to 70.92 grams per mole. Okay, so you can check now if you got the correct answer. Okay, so let's move on to the Dalton's law of partial pressure. So our previous examples, it only pertains to the individual gases. So ideal gas flows na diniscuss natin. We talk about it in its as individual gas. Okay. Yung sa Graham's law of partial pressure, meron tayong dalawang gas na doon. Okay? So, talking about pressure, okay? So, if we have to contain two different gases into one container, okay? So, the total pressure of that mixture of gas is equal to the sum of the partial pressures of the individual gases present. For example, we have this oxygen. If we add the nitrogen into one container, the total pressure is just the sum of the pressure exerted by the oxygen and the pressure exerted by the nitrogen. So we have total pressure is equal to pressure exerted by oxygen plus pressure exerted by nitrogen. Okay, so yung tawag dito sa pressure dito, this is called the partial pressure. Okay, so also PT total pressure is equal to total number of moles, okay, times R times T over V, where your PT is equal to the total pressure, PA, PV, okay, those are partial pressures, YI, mole fraction of each gas, Ni, mole fraction of each gas, and T is the total number of moles of the mixture. So, may question tayo dito, how do we quantify the contribution of an individual gas to the totality of the pressure of the mixture of the gases? Okay, so that is just equal to Yi is equal to Ni over Nt. The total moles of each gas, the number of moles of each gas over the total moles of the gas mixture, or it's also equal to the Pi over Pt, or that is also equal to the partial pressures of an individual gas in the mixture. Okay, so Pi is equal to Yi dt. So parang percentage ito. For example, this is a 0.4 of the total pressure. Yun yung pressure ng individual gas in the mixture. Okay? For better visualization of that concept, we'll have an example. So what pressure is exerted by the mixture of 2 grams of oxygen and 8 grams of nitrogen at 273 Kelvin in 10-liter vessel? Okay, so we write the given, the masses of the gases, the temperature and the volume are given, and required is the total pressure. Okay, using the formula, okay, the PT is equal to NT RT over V. So let's calculate for the moles of each gas muna. So Na pertains to the oxygen. Total moles of oxygen is equal to 2 grams of oxygen times using the molecular mass of oxygen. You can convert the grams into moles. So this is the moles of our O2. Same is true for the moles for nitrogen. Kinamit lang din ang molecular weight ng nitrogen. And then, calculate for the total moles, which is equal to 0.3482 moles. Substituting that to our main formula, we can get the total pressure 0.7804 atm. Okay? Alright. Okay, let's let's move on to another example. So yung kinalculate natin kanina is the total pressure given the masses of each of the gases in the mixture. Okay? Dito sa ating second example, we are given the or we are required to calculate for the partial pressure of 1 gram of oxygen and 1 gram of hydrogen gas at 27 degrees Celsius, occupying a certain volume, which is 2 dm cube. Okay, so the same method. So we are given this. So we have to convert dm cube to liter. So that's just the dm cube that's numerically equal. So 2 dm cube is equal to 2 liter din naman. Okay. And we have the concept of volume total is equal to volume A is equal to volume B. Kasi isa lang naman ang container nila. Okay? Isa lang. Nasa isang container lang ang oxygen and hydrogen. That's why total volume is equal to the volume of A and volume of B. So, let's calculate for the partial pressures. Okay? Knowing that partial pressure of the individual gases in a mixture is equal to the mole fraction of each gas times the total pressure. Okay, so let's not use that. Okay, wag muna. Okay, ang gagamitin natin, since the Dalton's law of partial pressure also obeys the ideal gas, the ideality. Okay, so we have PA is equal to NART over V. Okay, so Na, which is the moles of our H2 gas, that is equal to 0.03125 moles. So you can double check this in your calculator. Substituting that, we have partial pressure of A, okay, of the hydrogen, that's equal to 0.385 atm. Okay, so how about the partial pressure for oxygen? So the same. Okay, let's get the moles muna and then substitute it to our equation, and then we have our answer, 6.16 atm. Okay, right. So ano napapansin ninyo? So, mas mabigat ang oxygen, right? Mas mabigat ang oxygen kaysa sa hydrogen. Pero mas marami siyang contribute sa total pressure. So that is 6.16 atm. Samantalang sa oxygen ninyo, konti lang. Right? Yan. So mas marami kasi yung moles of hydrogen ninyo kaysa sa oxygen. Kahit pareho sila ng mass. Okay, so nagkatalo sila sa molecular mass. Alright, so let's have another example. So the mass percentage computation of dry air at sea level is approximately, okay, the N2 75.5%, O2 is 23.2%, argon is 1.3. So what is the partial pressure of each component when the total pressure is atm? Okay, so let's have a basis for calculation as 100 grams of dry air. Okay, so we have this given and we are asked to calculate for the partial pressures of A, B, C. Okay, partial pressure for A, let's assume that our A is oxygen. Okay, and then our B is nitrogen and C is your argon. Okay? Your argon. Okay? So, getting the individual moles of the gases ABC, okay, we have this. So this is C. Okay? And then adding that to get the total moles, right? Ayan. So, we have a basis for calculation since that is percentage kasi wala siyang unit. Okay, so this is just equal to sa buong 100 grams ng dry air, meron tayong 75%, 75.5% na nitrogen. So if we multiply that here, we get 75.5 grams. Multiply 23.2% to 100, ito din naman. Same is true for argon. So, don't get me wrong, yung basis ninyo ay ginawang 100 grams para kung ano yung value nito, numerical value, yun din ang grams nito. But you can use any number dito. You can use 1, 10, 20, or anything. Kasi percentage naman yan. Okay? Alright, so we have our total pressure. We already have our total moles and the individual. So we can calculate for each of the partial pressures. Okay? So calculated dito yung mole fraction of your oxygen and then nitrogen and then argon. Okay? Knowing that data, we can calculate for partial pressures of the individual gases sa air. Okay, so this is our answer. These are our answer. Okay? Yan, ganun lang. You can rewatch the video. Okay, you can pause it if you want para mabalikan mo. Alright? So, we also have our different formulas for the velocity. So, nabanggit natin yung velocity kanina. We have what we call the average velocity and the root mean square velocity. Okay, so the average velocity from Maxwell equation is equal to square root of 8 RT pi m U, okay, molecular weight. So, ang variable lang natin dito is temperature, molecular weight, and velocity. Okay. So, we also have our most probable velocity. So, these are other kinds of velocities that will describe the particles, okay, inside the container. Okay, so let's cut our lecture for today. Next na natin pag-uusapan will be about liquids. Tapos na natin ang gases. So, for next lecture na yun. Okay, thank you for listening. If you have any question, pwede kayong mag-chat sa akin. Thank you.